Yeah.
Cool.
I see we have people joining in. Let's give them a minute before we go live. We are now live. Hello, thank you for joining us today. My name is Kuber Rizwan and I'm here from Buddha Science Studio. Before I introduce our speaker for today, I want to actually show you guys something that we've been working on. It's basically a large language models bootcamp, which is exclusive for enterprise-based applications. As you can see that we have top-tier industry leaders that are partnering for this bootcamp over the year, and the last one is upcoming soon enough. So you can get the dates from her. As you can see, the curriculum is super, super exclusive and comprehensive, and it is dynamically updated according to the industry. So make sure to visit the web page, and you'll get the link in the chat box as well. We got 5% off as well, and you can get best deals for the LLM bootcamp if you desire to join us by booking an advisor call as well. So you can navigate to the page, and if you have any questions, you can request for it definitely, and we will definitely be capable for it. In today's session, we have Karun, a senior data scientist specializing in NLP and computer systems with experience at Dell Technologies, Amazon, and Walmart. He focuses on optimizing personalization and enhancing e-commerce solutions. As a data science mentor at Cognitive, Karun has successfully guided over 50 candidates into their first data science roles. So thank you so much, Karun, for taking the time to join us at Data Science Dojo. And without any further ado, over to you now. Thank you.
Awesome. Hey everyone. I'm hoping my audio is a bit better. Let me know in the chat. If it is, I'll start with the screen share. Awesome. So, yeah, hey everyone. Welcome to sort of the recommender systems webinar that we have for today. We're going to be covering a bit about how recommender systems came into being, how the current state of recommender systems looks like, and where we are sort of going next. So before that, just a bit about me. My name's Karun. I started my career as a software development engineer back in India. I was part of Dell Technologies. A few mentors there helped me get into analytics and then into machine learning. And I reached a point where I felt like a master's would help. Did my master's in data science at CMU and worked at Amazon as a data scientist and applied scientist for about 2.5, 3 years. Now currently working as a senior data scientist at Walmart. I am a creator on LinkedIn with about a 40K following, and I also help folks with free mentoring on TopMate. I've completed nearly 10K sessions. Both of my links will be available post the session in case anyone wants to reach out to me or sort of follow my content on LinkedIn. Cool. Now coming to sort of like the topic of the day, recommender systems. So starting out with how exactly did recommender systems come into being, or what sort of customer problem motivated this? So around the 70s and 80s, the internet was gaining a lot of momentum and a lot of information was essentially available at the hands of users. So the result of an increase in information was a user problem, which is how to exactly find information that is relevant to me. Initially, this was solved using search and retrieval systems, where the idea was that the user provides an input and the content that they want, whatever sort of like text matching based or keyword based, the system tries to find the most relevant content for the user. And a lot of search systems came into being sort of in that manner. Google was the most popular one with what we call like the page rank model at that time, and sort of established itself in the late 90s. Now, search and retrieval helped users discover the things that they want or fetch the things that they want. But there was also a group of people working on a branch of this problem, which was that, hey, since the user is sort of interacting with the website often, we sort of have an idea about what they like or what they don't like, or what they tend to interact with more and what they tend to interact with less. So knowing this, can you actually provide more recommendations to users based on their previous search history? And that's sort of how the recommender systems came into being. In terms of like how did it start out? It initially started out in 1992. Group Lenses, sort of like a research group. They started out with a research group slash they were working on a news group slash forum, online discussion forum. So based on what folks interacted with in those forums, they would get more recommendations that were relevant to them. Like if they interacted more in sports, they get sports recommendations, political recommendations. And it essentially, the underlying model was sort of a collaborative filtering model. What exactly is collaborative filtering? We'll go into that a bit deeper as the session progresses. And similarly, during that time, around the same time, MIT Media Lab, another research group, in 1993, they sort of produced this solution called Ringo, which essentially based on users' music CD purchase history. They could provide future recommendations of what kind of music that they would actually like. And this was pretty seminal, primarily because it proved that this idea of a recommender system has commercial value. And when you essentially prove that a research idea has a lot of commercial value, then the pace sort of picks up. And that's what we see later on. Now, before we dive into sort of the present state recommender systems and future state recommender systems, a quick aside on the basics of recommender systems, starting with content-based filtering system. So content-based filtering systems are it's sort of like the most common type of recommender systems. The idea being you provide recommendations to the user based on the attributes of the user or the item. Essentially, if they like a certain item, what are the attributes of that item? Similar items you recommend to the user. Or if the user has a certain attribute, you make recommendations based on that. There are a few types of content-based filtering systems, starting with demographic-based systems. Demographic-based systems, for instance, like Netflix, if you log on to Netflix from somewhere in the US, you would get a certain set of top 10 movies. But if you log on from somewhere like Korea, you might get a different set of recommendations. A bit of it is because of what content is geo-blocked, but a bit of it also goes into what's trending in that particular country. Another one is utility-based filtering. Essentially, like I mentioned, if you like a certain item, whatever attributes of that item are, you will get more recommendations. Like, for instance, right now Halloween is going on. If you interact with a lot of Halloween items, you'll tend to see more recommendations of Halloween items on your feed. And the third type of content-based filtering is knowledge-based filtering. So here, it's more based on the information a user provides. Like a common example for folks might be a shopping website like Myntra or Amazon, where they essentially provide or ask you to, or provide the facility for you to fill in a lot of filters. And based on those filters, they can improve the relevance. Um, you provide a lot of you use essentially a lot of filters to do your search. Those filters essentially get incorporated into the recommendation system, and they're able to get a sense of what it is that you're looking for, and based on that they essentially provide better recommendations while you're searching through the website as well. So these are the basic types of content-based filtering systems. Content-based filtering is one category of recommendation systems. The second category is collaborative filtering systems. Now, again, like we discussed in content-based, there are three types. Collaborative filtering also has several types. The two main types are memory or nearest neighbor based systems. The idea here is, if you as a user, you like a set of items, there may be other users also who like a different set of items. If you and another user like the same items and dislike the same items, then there's a good chance that if the other user liked something, you would also probably like it. So that's essentially the idea behind memory or nearest neighbor. Um, Whatever the other users that are similar to you have liked, you will get that recommended to you. Maybe just going over a quick, within memory based, there are two types as well. It's user memory based collaborative filtering, and item memory based collaborative filtering. So user, like we discussed, let's say these two users, A and C, they've liked similar things, they disliked similar things. So now if user C has liked this particular product too, then you can say with a certain amount of confidence that maybe user A will also like that particular product. Again, we're taking just few examples. When you scale across multiple users, across multiple products, that pattern becomes a bit more stronger. But this is like the basic idea behind user collaborative filtering. And how you check if two users are similar. You can use anything from as simple as cosine similarity to something more complicated, like building out an embedding based model and using a classifier on top of it to predict if you should recommend something or not. It could be either way, but the idea remains the same. What's similar, identify users similar to you, and what they have liked, you will also probably like. Item similarity is sort of the same way. You identify items that are similar to one another. So let's take 4 and 6. So these two items received negative reviews a lot from certain set of users. These two items also received positive reviews from certain set of users. So because of that, because of the way that they're rated, maybe they are sort of similar to one another. You can also put in like content-based filters as well. But the idea being, if let's say this particular user 5 essentially liked this particular item, then it's possible that the user would also like item number 6, just because of the way other users have reacted to that item. So this is sort of the memory-based model. Memory-based models are fairly good in terms of capturing local trends. What exactly is local trends, we'll go into a bit later on, but the idea is they sort of memorize the patterns and they try to leverage what they have memorized to provide you recommendations. Now, coming to model or metrics factorization based methods, these work in a more general capacity. The idea again is, or the assumption is, that if you create a user item interaction matrix, a matrix of this form where you have users along the rows and items, or let's say products along the columns, and you fill the matrix out with the ratings users have provided for that particular item or product. If you have a matrix of this form, what they hypothesize is a matrix you can sort of decompose into two different matrices. Like the product of these two matrices would result in this matrix. And they're saying with enough data, with enough iterations of an algorithm very similar to gradient descent, you can get the values in this matrices to represent latent attributes of users or items. Essentially, this matrix essentially has the same number of rows as this. So they're saying this represents the same user, and the values in these columns represent latent attributes of the user. It could be something like that user likes a fantasy genre. Like, let's assume that this is a movie data set. Um, the the person likes fantasy genre. They maybe like newer movies compared to older movies, anything of that sort. So those attributes or preferences of the user essentially is represented by these numbers. That is what they are hypothesizing. Explainability is a bit hard to do, especially in recsys, which again we'll cover later. I mean, we'll talk about that a bit later, but they're hypothesizing the same. Similarly, for items, if you see here the number of columns in this original matrix and the number of columns in the item matrix are the same. So what they're saying is each of these columns represents one item, and the values in that represents the latent attribute of that particular item, like the fact that it is a sci-fi movie, or the fact that it is a new movie, or the fact that it is maybe has a female lead, stuff like that. So each of these attributes or values represent a specific latent factor of that item or latent factor of that user. And if you can generalize or extract out those latent factors, then you can fill back in any missing value in this matrix. Being that, let's say this user hasn't rated this item, by getting the dot product of these two, the matrix multiplication of these two, you can actually fill this value back in. So that's essentially the idea behind model-based collaborative filtering. This is capable of extracting more general patterns, and this is capable of memorizing things better. So these are like good takeaways to keep as we sort of proceed along in the session. Now, a final aside in recommender systems is talking about the metrics. So the metrics and recsys have evolved over a certain period of time. So we initially start with the accuracy metrics. So like assuming that you have a rating data set, the idea is you want to predict the rating for a future user item pair as close to what the actual value is. So it's essentially like the same metrics that you use in a regression problem. So you can use mean absolute error or mean squared error. So those were the metrics that were dominant for a good amount of time. But as the research evolved, they realized that as you build out a recommendation system, you're providing recommendations in a ranked order. And the ranking really influences how the user experiences the website. So all the recommendations you make or all the rating predictions you make doesn't matter. Only the top 10 or top 20 ratings, top 10, top 20 items that you rate in the order that you rate actually matters. So they wanted to move away from the accuracy based metrics, where it could be that you build a really good model, but it's good at predicting like the 3-star or 2-star ratings and not really good at predicting the 5-star ratings. But 5-star ratings are what you're going to recommend to the user. So they switched over to ranking metrics. Ranking metrics are very similar to classification metrics like precision, recall, F1. The only thing being that instead of looking at the entire set, you only look at the top K set of items. So it's called precision at K, recall at K, F1 score at K. And there are a few others. So precision and recall doesn't really take into consideration if the relevant item that the model predicted came in the first position or the fifth position. Because if it's there, it's considered one against the true positive. If it's not there, it's not considered. You get a zero value in the true positive. So it doesn't take into consideration where in the recommendation list it's actually located. And that's where things like NDCG come into play, where the position of the recommendation, of the relevant recommendation, does matter. And those would be like another way to represent the performance of your system. So a takeaway from here is don't use like basically accuracy metrics. A good set of metrics to use is mean average precision and NDCG. These would be at k values of maybe 10 or 20. These are good. These are sort of the benchmark or standard metrics in the recsys, and it's good to sort of keep in mind while we go forward in the session. Now, apart from these, there are a few other ways in which you can assess the recommender system. The first is a diversity metrics. Essentially, you don't want to end up recommending the same set of items to every user. You want it to be personalized to a certain extent. Like it could be that let's say when Netflix acquired all the Marvel catalog, uh, for everybody it ended up recommending like 5 Marvel movies. It could be a good recommendation, but it could be possible that there are a group of people who maybe they don't like Marvel, so to them the recommendation doesn't make sense. So it's a good idea to personalize the list quite a bit to the user. So diversity metrics essentially evaluate that. Essentially, it looks at how different are the recommendations between two users and how different are the recommendations made to a single user. Like if let's say you make a recommendation for 10 movies, if all 10 are Marvel movies, that's a pretty shoddy recommendation in a sense that you're recommending essentially the same item, just different versions of it. Or maybe in Amazon, you're recommending 10 different versions of an air fryer. Again, may not convert as well as you would want it to convert for a business use case. So inter-list diversity is the diversity between two recommendations made to two different users. Intra is within the same list. Um, Coverage is basically how much of the catalog you're actually recommending. You want high coverage, but you don't necessarily need like 100% coverage. And user coverage is how many relevant recommendations can you make to users. Like sometimes you may not have any confident recommendations you can make to certain users. You want to decrease that as much as possible. And finally, online evaluation metrics like click-through rate, conversion rate. These are the metrics that are typically tested in your A/B testing, and these are sort of the golden standard for whether a recommendation system is actually improving stuff or not. Cool. So now that we have like a foundation of the past or the basics of recommendation system, we have three methods, like I mentioned: content-based, collaborative, and hybrid. I think I skipped over hybrid is nothing but a combination of content and collaborative. So these three are the main recommender systems. And in terms of metrics, we have the basic metrics for performance are recall at K, precision at K, mean average precision at K, NDCG at K, etc. And there are a few diversity metrics, there are a few metrics for coverage, there are a few metrics to there are even more metrics for bias and stuff like that. But it's always good to maybe mix in a few of those metrics to make sure you get different flavors of assessing your particular axis. Now, coming to sort of the current state, or what we call second and third gen recommender systems. Actually, second gen may not be as prevalent in a lot of companies, but we'll cover them albeit. So the second gen, the first seminal work in second gen recommender systems is by Amazon. It was a paper released in 2003 where they essentially moved from a user collaborative filtering model. If you remember, it's one of the memory-based models. So till date, a lot of recsys were using user-based collaborative filtering. They shifted over to item-based collaborative filtering. So why did they do that? One, Amazon was exploding at that time. They were getting a lot of users. So when you have a lot of users coming in, the number of ratings that a user provides for a particular item is very sparse. So comparing two sparse vectors is actually quite hard, because a user might have rated like 3 out of the 100,000 items in Amazon, and another user might have rated 3 of the 100,000. Now, whether these three match, it's basically a shot in the dark. And if they don't match, you can't actually find users who are similar to this user. So they decided to, so that was one reason. And the other reason was, again, the number of users at that time in 2000s far outweighed the number of items on Amazon. So they couldn't scale the user-based model. So because of this reason, they decided to try out the item-based collaborative filtering model. Essentially, every day they calculate the item similarity and they store it. So now if a user essentially liked a certain item, let's say for the user we have recommendations of um, this maybe 10 or 20 items the user has rated. And we know that for this particular item, these 5 items are similar to this particular item. So the rating that this user might provide for this item, what they hypothesize is it's going to be an average rating of all these similar items to this item. It's not a simple average, it's a weighted average. Essentially, more similar the item, more weightage this rating will have towards this predicted rating. Um, but the basic idea again was the switch from looking at similar users to similar items. One advantage, the catalog doesn't expand as much every day, so they could actually calculate item similarity on a daily basis, store it, and then read it sort of out of a DB. There are like a few tricks to make that faster, like the fetch for the top 10 or top 20 similar items for a particular item. To make that faster, there are certain tricks and performance hacks. But the key idea being that they switched over to item. So A, it became more scalable, and B, they actually saw a performance improvement primarily because for a particular item across users, the number of ratings for a single item actually was it tended to be less sparse than compared to the user vector. So the item vector was essentially less sparse than the user vector on average. And there are definitely certain items that didn't have a lot of ratings and they would be sparse, but on average the item vector was less sparse. So because of these reasons, because of the fact that you could pre-compute, because of the fact that the performance was good, this model sort of became very similar, and a lot of e-commerce systems and other solutions started adopting item-based collaborative filtering. Now, coming to the next work that was fairly seminal was collaborative filtering for implicit feedback. So till this point, we've basically seen explicit feedback. So explicit feedback is essentially when a user leaves a specific review for an item, like a 3-star review or 4-star review, or on YouTube, you hit the like button. At the same time, now explicit feedback is kind of rare. A lot of users don't leave reviews. A lot of users don't hit the like button. Because of these reasons, as you scale, you essentially, if you have more data, if you have more feedback from users, you would be able to make a more performant system. So they realize that if they actually tap into the clickstream feed, they actually will get implicit feedback from the users, in the sense that they'll know what the users interacted with, like video watch time, or they'll know what the users clicked, like on a product, did they click it or not, did they go through the PDP page or not, the product description page or not. So those are sort of implicit signals. It doesn't necessarily mean that the user didn't like the item, but it's more relevant than a user maybe not watching the item, not using or not interacting the item at all. Now, just because the user didn't interact with the item doesn't mean it gets a negative score. But the fact that they did interact with a certain item, it's somewhere between this 0-1 scale. Now, they did sort of like use a lot of statistical measures to come up with a confidence score. Essentially, if a user interacts with the item more and more, or if they interact with a certain set of similar items more and more, this confidence score gets higher. And they were able to use this confidence score in sort of metrics factorization. So earlier, what we covered was a memory-based system. This is a model-based collaborative filtering system. So in the rating metrics, or what we used to have as the rating metrics, they essentially used these confidence scores instead, that they derived from the implicit feedback. And again, the approach here is a metrics factorization based approach. They have a method called ALS, alternating least squares, for like I mentioned earlier, the metrics factorization sort of decomposes this matrix to two different matrices. And how do you determine the values in this matrix? It's very similar to a gradient descent sort of approach. Alternating least squares sort of fixes one matrix and then tries to figure out the best parameters for this matrix, then fixes this matrix, tries to figure out the best parameters for this matrix, and it does that again and again. So it's very similar to gradient descent in like the conception of, or the idea. And the basic idea is to again get the best scores possible in those metric cells. And essentially they were able to prove that the same metrics factorization model, explicit feedback versus implicit feedback. Implicit feedback actually does provide a performance improvement in multiple metrics sorry, matrices that they actually considered. And yeah, this became sort of standard. The fact that you can actually use implicit feedback, companies started getting feedback from clickstream. So every click, every scroll, every video watch time that you use is probably monitored at this point, and they use that to improve their recommendation system. Now coming to the sort of the final model in this second generation system, which is the factorization model. So till now we had talked about the fact that there are two different collaborative filtering approaches. One is the memory-based one, and the other is the model-based one. So the memory-based one is really good at remembering stuff, essentially what they liked and what they didn't like. And the model-based one is really good at generalizing, at identifying latent features or general patterns across all the data. So till date, till like this particular paper came out, which is in like 2008, a lot of people had tried combining both so that they could get like a short-term memory and a long-term generalization capacity to combine both, essentially combining the memory and model-based systems. But this was actually the first paper to actually do that. And this paper also adapted explicit and implicit features, explicit and implicit feedback into their data as well. So it was essentially a combination of all the work done thus far, and it was one of the papers that actually worked on Netflix data set, and it got really good results on Netflix as well. And this paper also had another sort of innovative part. Most of the other works were sort of a combining all the other work that had been thus far and proving that it can be performant, it can be effective. But the innovative part of this paper was that this was the paper that brought in the top K based um, uh, evaluation metrics. Like we discussed earlier, metrics can be of a few different types. Till a certain point, only accuracy based metrics were used. And this paper, the factorization machines, was the paper that sort of popularized ranking metrics and the fact that you should be only evaluating the top 10 or top 20 or top 50 recommendations that you make, and the bottom recommendations, whether you get it right or wrong, it doesn't really matter. So another seminal paper, and factorization machines are quite common nowadays, in the sense that the idea of mixing in multiple systems is quite common, and most companies that have been around for a while, at least, you will see sort of this hodgepodge of a lot of different systems and essentially ensembles that can actually provide better performance. Now, coming into the third gen systems, or what we consider present day systems, the 2020 systems. So in sort of like early 2010s, we saw like an uptick in two trends. One is deep learning and deep learning becoming effective, and the other is cloud computing and the fact that compute became a lot more cheaper. So this led to a couple of trends. One, the infusion of deep learning within recommendation systems, and two, architectures that became really common are the wide and deep neural networks, and the other one is the two-tower neural networks, also known as neural collaborative filtering layer neural networks. So the wide and deep neural networks essentially incorporated the idea of factorization machines within neural networks. So the idea is that you take all the features and you can pass these features uh, through a deep neural network and pass it to the final layer, or you can take all these features and do a cross product of those features and pass it to the final layer. The idea being that certain features you can get a memorized intuition of what the user likes from them, and certain set of features you want them to interact so that you can get a generalized view of what the user likes. Very similar to factorization machines. This was a concept that was sort of innovated and or found by Google researchers, and for a time it was part of some of their systems. What's part of the systems currently, nobody has like a clear picture. It tends to lean more towards the second type of models, the two-tower models, but wide and deep learning was fairly popular. And essentially, what we talked about in the factorization machines, combining these two methods of memory and model, that's essentially what the wide and deep neural networks are doing. Two-tower neural networks, the idea was You can essentially, or you have a neural network or a neural tower for each of user and item. So the user neural network or user tower essentially encapsulates all the information you have about the user, the demo information, you use an ID to identify the user, and you can put in all the user attributes through that particular neural network. And the item tower or item neural network, you pass in everything you know about the item, including the ID of the item, and you essentially encapsulate at the end all the information that you know about the item. And finally, you sort of make a call, the final embedding that you get from the user tower and the item tower. You typically do a dot product. Dot product, for some reason, is very effective. You do a dot product to figure out if this particular user would interact with this item or not. You get a probability score, you get a rating. Either way, you can determine that in your final layer. And then the paper that sort of made it popular was called a neural collaborative filtering paper. It's linked in the slide. Both the papers are linked in the slide in case anybody wants to dive a bit deeper into it. And the final sort of trend, or I wouldn't say final, the second last trend that we sort of saw in present day systems was the graph recommender systems. So essentially, till this point, the recommendations that we made were based solely on what the user liked or not. And the sequence in which the user moved through the website didn't really matter. But latest research has shown that the sequence of items that the user interacted with before um, is really important in determining what the user will like next. So this idea of sequential recommendations, session-based recommendations, all of these things came into picture. And one of the dominant networks in this is graph neural networks. The idea being that you can essentially, from each item, you represent each item as a node, and there is a path from one item to another item if the user actually went from that viewing that item to the next item. And this helps predict what the user will like next. Graph neural networks are a bit harder to implement in the sense that you need a lot of compute. Graph Sage, popularized by Pinterest, was one of the main architectures that was sort of seminal in the space. It's linked in the slides, and in case like anyone wants, they can definitely deep dive into it. And yeah, the final sort of trend that's still being used in most systems is the phased recommendation system. So irrespective of however you build your recommender systems, current day production recommender systems usually provide recommendations in phases just because of the sheer scale that they're working at. So usually they have items and users which are in the millions or billions of ranges. They have a model that they call the candidate generation model that they usually run once a day. And this works over the entire like million billion space to identify for each user a set of maybe 100 or thousands of items that they are likely to interact with. So every day it runs and it sort of decides that set of items, 10,000, 1,000 items. Then it passes through the ranking model. The ranking model takes in the context, like session-based context of what the user is currently interacting with, hourly context, any of those things to sort of figure out within those 10,000, 20,000 items, how do we re-rank this list so that within this, what is most important to the user at the moment, how can we provide those? There can be other re-rankers as well, which again, based upon business knowledge, seasonality, stuff like that, you can change around what's there in the list. So this is typically the phased recommendation system is pretty standard, and you will see it in almost every company. Different one team will take care of the candidate generation, and other teams will work on like building out rankers and ranking models. Now, if anybody is sort of interested in getting into recommender systems, TorchRec is a really good package that you can start with. MovieLens is a good baseline, and this sort of like a resource that I'm linking, a blog that I'm linking, pretty much covers all the recommendation system, past, present, and future, and it'll definitely give you guys an overview. And what challenges are there in recsys currently? Like if you want to get into recsys, what would you be working on? One is definitely multimodal. We're moving away a lot from text and taking into consideration video, short form videos, combining with a lot of social media trends and stuff like that. So multimodal, being able to work on multimodal data is really important. And like I mentioned, getting a lot of those extracting information from social media and identifying trends that are going on and trying to capitalize on those short-term trends is also really important. Sequential and user intent-based sessions, like if is the user in a gift giving mode, or is the user currently searching for maybe some kind of utility-based item. It's starting to rain here, so maybe a lot of folks are searching for like finding an umbrella, raincoat, stuff like that. And another sort of like area that you could be working in is just the re-ranking part of it, based upon the business model, based upon what business wants to optimize at the moment. Maybe Halloween is going on, they want to push sales for those kind of items. So you want to adjust your re-ranker to make sure that in the recommendation panes, some of those Halloween items start popping up, or there's a clearance sale going on in a few of the stores. You want to make maybe pop those out in the recommendation panes. So that might be something you're working on if you get into recommendation systems right now. And the final thing is bias and explainability. A lot of folks want to make sure that recommendation systems aren't biased to only recommend like what's popular, but rather actually recommend what's personalized for the user, and explainability in the sense of why do we make the recommendations that we make. So yeah, and these are like some of the areas that you might be working in if you venture into recommendation systems in the industry right now. And I think that's the end of the session. Happy to take any questions if there are. Um, what are the advantages of using a two-tower model in recommendation systems? Advantages in the sense that deep learning models do tend to be able to capture a lot more information and generalize a lot more information. Apart from that, I wouldn't say any specific advantage. Um, so for instance, if you're moving from two tower is sort of standard, and most companies do use two-tower models, primarily because you can input in a lot of the attribute-based information. You can input in a lot of the user interaction is information into that, and that way you can combat a lot of cold start issues, because you have like attribute information into it. So if a new item comes in, you can figure out what items are similar to that item and provide recommendations based on like for that new item, what kind of users did interact with it. So cold start issues are solved. And the fact that the deep learning network sort of creates like a really good, hopefully creates like a really good user embeddings and item embeddings, you can leverage that as well. And again, it's a really flexible network, because you can put in those embeddings, you can make it multimodal by putting in information from like stuff like video, images, or like from social networks. If you're extracting some information, you can again throw it into the network and let it create the embedding. So the idea that embedding hopefully encapsulates a lot of information. So, I would say it's very similar to LLMs, and actually LLMs are also a lot of the large language models have been used in like trying to encode this information. A recent paper that came out from I think ByteDance, they used essentially an LLM to encode the item and another LLM to encode the user, and they found like near SOTA results. So essentially what they're trying to do within these two towers is incorporate world knowledge and incorporate user information, create a user embedding, incorporate world knowledge, incorporate item information, create an item embedding, and try and see how those embeddings react. Our graph recommendation model, a deep neural network, how you optimize it? Yes, it is a neural network. It's just that in typical neural networks, you have like like in recurrent neural networks, there are loops. In feed-forward neural networks, it flows straight and flows backwards. In graph neural networks, the connections are directional, and they don't necessarily flow like forward propagation, back propagation doesn't necessarily work in the same way that you would see in a normal neural network. But yes, for us, like if you're more focused on the applied part of the data science, there are packages that will pretty much do it for you. And yeah, if you're interested in graph, Sage is a cool paper to start out with. Why can't we use MA and MSC, but metrics like precision or recommendation for top key items? So essentially what we're MA and MSC is for continuous values. You're essentially trying to see how far off your rating prediction is from the actual rating prediction. So let's say you have three items. So the one item actual rating is 522, and the ratings that you're providing is like 322. So you are accurate on the low two items, but you weren't accurate on the top item. Which essentially means that your model, when you make the recommendations, you probably won't make the right recommendation. So you want to be accurate on the items that the user is likely to actually interact with. So that's why precision and recall come into picture, and you use the fact that whether it was in the top 20 or not. So essentially a 0 or 1, which is why precision at K, recall at K, those kind of metrics come into picture. Can you please go through the following challenges in section 1, social network, sequential user intent, and re-ranking for business logic? Um, Basic idea, social networks. The idea is you want to capitalize on short-term trends. Like if something is going on TikTok or Instagram, you want to try and grab keywords, grab hashtags, try and decipher video, stuff like that, and maybe use those to try and figure out what to recommend, what not to recommend. Like it's Halloween, maybe like things like pumpkins and pumpkin spice lattes, or like earlier when kids were going back to school, they had this thing of like gifting teachers like stationery and items. That was like a trend on TikTok. If we could capture that trend and have like have push like stationery items or like bundles on websites, that would be really cool. So that's like capturing social network, sequence and user intent sessions. Essentially, let's say, okay, based on like whatever the user has interacted with before, you have provided a few recommendations, maybe like recommendations for a few tech items, a few sports items. I mean, let's say I typically like tech and sports and books. So they have provided tech items, sports items, and a few books in my feed. But now since it's like maybe Halloween, I'm looking for decorations or candy. So within the session, they get the information, and they re-rank the item so that they can push into the recommendation systems, that they understand that, okay, the intent in this session is more around maybe holiday or gifting. Let's switch out the recommendations from what he normally does to focus in on this. So that's more session user intent, session based recommendations. Re-ranking for business logic, again, like I mentioned, clearance is like a good example. If a clearance sale is going on, what the business wants to do is they want to move out stock as fast as possible so that they don't have to take in the inventory cost. So if items are going on clearance, you want to maybe recommend them onto your website as well so that they sell out fast, inventory cost remains low. Is transformer architecture involved in recommendation system designing? Yes, you can definitely use transformer architectures to create the embeddings. And like I mentioned, like ByteDance recently came out of the paper where they created an item LLM, a user LLM. They essentially used the Llama model. Llama is sort of transformer based, or I mean, it's at least based on the architecture, they are using a transformer based model. So yeah, you can use those transformer architectures to create embeddings. Are recommended systems tightly coupled with data models used during implementation? Uh, I'm not sure I understand the question. Tightly coupled in the sense that most ML systems are tightly coupled with data models. Like machine learning learns from data. So not 100% sure. Like it's a flaw of most ML system design, ML system architectures, that they're tightly coupled with their data systems. If the data changes, the ML model will start spewing garbage. They expect the predictions to remain fairly normal. Um, you mentioned graph recommendation does not use forward and backward. How are they? No, it uses forward and backward. It doesn't work in the it so in feed forward neural networks, you have the connections that are moving like left to right, or in recurrent you have connections that are moving up and down, and there are like recurrent connections. In graph, it's a directional graph, so it's still back propagation and everything. It's just that it doesn't move in the same way that you would visualize. But yes, if, forward and backward, all of that still happens. There are questions in the QA tab. My bad. I Where would I access the QA tab? My bad.
Am I audible, Karan?
Yep, yep. Oh, yeah,
Yeah.
I've just got the
So
keyword up. Yeah, yeah.
yeah, it's on the top.
Cool, cool. Yeah. What type of strategies might TikTok be using for recommendations that would give them an advantage over other recommendation systems? They're actually using TikTok is more short form videos. So they have these architectures called query interest network and PRR. They actually came out with a paper recently on short form video and how they're doing personalization in it. Drop a DM on LinkedIn and I can share that paper. But yeah, it's it is DL based, it is embedding based, but it's not just one method. They have like three methods within their system. And primarily because it's short form video, there's a lot more feedback that they get, which is why I think primarily they work a lot more. And more than the modeling, it's about how fast their models adapt. Like they have this idea of like pushing to a sample, seeing how the sample reacts. If the sample reacts well, then they push it out further. So it's more for like a phased launch, which I think is like it's not just the machine learning, it's also the engineering aspect that works well with TikTok, I think. Why can't we use MA and MSc, but metrics like precision for recommendation? I think I answered that. How good are LLMs at making recommendations? Um, from what the paper describes, like the paper from ByteDance describes, it's getting SOTA results in sequential recommendations. So pretty good. The problem is their A/B testing results are a bit vague in that paper. So I'm guessing more people will try it out, and we'll have to wait and see how good it actually is. Graph recommendations model, yep. How do they benchmark the results for accuracy before they are published? So usually movie lens is like a good benchmark data sets. There are a couple of benchmark data sets in recommendation systems, and what they do is they run the models from previous papers on that, get the metrics, and they run their own proposed model, get the metrics, and showcase sort of how the models compare. Do you have a link to the ByteDance paper? Thanks. Drop me a DM on LinkedIn and I can share it. I think the paper is hierarchical large language models, HLLM. That's the title of the paper. So if you Google it, hopefully you should get it. Um, awesome, awesome. I think that's all the questions on chat. Anything else? If not, I guess we're at the end of the session.
Perfect. We are, and Karan, just to be clear, I'm audible to you, right?
Yep, yep.
So
Now it's clear.
once again, sorry to the audience that my voice was not clearly audible for all of you, but thank you so much, Karan, for a very insightful talk. And I hope that the knowledge that you have shared is truly beneficial for the audience that has joined for the session, the entire session. Moreover, I'll just show my screen and repeat what I exactly said about the large language models bootcamp. It's basically a super exclusive LLM bootcamp. It's last one for the year. So don't forget to check out our webpage for this. And it is super comprehensive and detailed in terms of curriculum. So you can check the page out. We have 5% off for a limited time. Moreover, you can also book an advisor call if you have issues with the budget and all. So we can give you the best possible package. Moreover, feel free to join our formal community, official community of Discord. Here you will be getting the exclusive content, the giveaways, and all that. And we have all of our alumni and the industry partners added to this community as well. So you will have the access to the exclusive content. So don't forget to join our community as well. And likewise, thank you so much, Kiran, for a very truly wonderful talk. And we hope to see you again. Thank you so much.
Awesome. Awesome. Thanks, everyone. Bye.